Next thing we do is look at theorem 3.3.3 in the book about algebraic limit theorem, so it's called the algebraic limit theorem. And what it says is what you would expect. It's a summary of all the properties that you actually remember, well, you probably remember from all your undergrad courses. So we assume that we have two sequences, both converging to some limit, some numbers. Limit when n goes to infinity of an is equal to a, and the limit of bn as n goes to infinity is equal to b. Then we have one, that the limit of a constant c times an is just c times a. And this is true for all C in R. Second property is that the limit of the sum is the sum of the limits. So A plus B. The third thing is that the limit of the product is the product of the limits. And here is just a corollary of this thing. Is the limit of the quotient is the quotient of the limits, provided of course that this fraction makes sense. So provided b is not equal to 0. Okay, so we are going to prove a few of these statements, and a couple of these, and the rest are going to be left to you as exercises. You should read them and try to reproduce them on your own. Okay, so what is it? So first of all, for part I, what we know, so this is what we know. We know that for all epsilon greater than 0, there exists some n, n in n, such that a sub n minus a is less than epsilon for all n greater than or equal to n. Okay, I'm just gonna write it for all n greater than or equal to n. I'm gonna write it in this more. in this more succinct way. This is the actual definition. I mean, the other one is correct, but this makes it actually more clear. And for application, this is what you should keep in mind. So this is where every quantifier is. For every epsilon greater than 0, there exists an n, such that for all n greater than or equal to that n, the distance between an and a is less than epsilon. This is what we know. What do we need to show? We want to show that, well, the limit of c times an is ca. So you want to show basically the same thing, except that inside the absolute value, we're going to have c times an minus c times a. The new sequence is can, and the limit is supposedly ca. This is what we want to show. So this is not known. What's above, so namely this, is known. And we want to show what is here below. Okay, so this is the statement we want to prove. So this looks a lot like the one above, except that there's a c here. But what helps us to show this is that here we have a quantifier. It's starting from what we know, so for all epsilon, so first of all, we want to show this for all epsilon. So this is what we want to show. So we start with, so let epsilon be greater than 0. This is an arbitrary epsilon. Whenever you start a proposition with for all epsilon, you want to show that, whenever you try to prove a statement involving that, you let epsilon be greater than 0 be an arbitrary number. Here it's an arbitrary positive number. But so let epsilon be greater than 0. Now this is epsilon is going to be fixed from now on. Now we use the definition above. We know that for any epsilon greater than 0, this happens. So for all epsilon greater than 0, this whole thing happens. But epsilon is anything. So we know that epsilon over c is an admissible number here in this statement. Just the fact that we're using the same letter, it doesn't mean anything. It's just any number for all number greater, you can call it whatever, alpha, beta, whatever, greater than 0, there exists an n such as blah blah. This is a number. The only important thing is that that number is a positive number. And this is a positive number. Know that epsilon over c is greater than 0. Epsilon over the absolute value of c is greater than 0, right? And so there exists, and therefore there exists an n associated to that particular number, associated to that epsilon over the absolute value c, such that for all n greater than or equal to n, a n minus c is less than epsilon over c. Oh, actually, here I made a mistake. So in small mistakes, it's not really a mistake. So it's imprecision. So here, when c is equal to 0, there's nothing to show. So 0, you get the 0 sequence, which of course converges to 0. If c is equal to 0, then this is 0, and this is 0 as well. So we start, so case 1, or okay, let me just say, so the case C is equal to 0 is trivial. Let me just here, so here the case C is equal to 0 is trivial because of the reasons I just said. So we assume C is different from 0. So it could be either positive or negative, but not equal to 0. And then we'll let some epsilon be greater than 0, be some arbitrary number. So for all n greater than or equal to n, a n minus c is going to be less than epsilon over c, which implies, I mean, this is just some basic algebra, that c will be multiplied by the modules of the absolute value of c on both sides. Oh, this is an minus a, I'm sorry. The absolute value of c times an minus a in absolute value is going to be less than epsilon. But this is equal to c times an minus ca. So we've shown this statement for every, I mean, to be true, the statement that for every epsilon there exists an n, such that for all n greater than or equal to that capital N, can minus ca is less than epsilon. The only difference here is that the n that we choose down here, the capital N, is the n up here associated to epsilon, not to the same epsilon, but to epsilon over the absolute value of c. Here for each epsilon we have an n. For epsilon over the absolute value of c we have some n, and that's going to be the n that we need down here for epsilon. Okay? The n that we need for epsilon over the absolute value of c up here is going to be the n we need for epsilon. So that proves I'm sorry. For the second part, this is the so we have again we start with what we have. To just keep in mind that sorry, we keep in mind I mean, it's very important that whenever we want to show something, we keep track of all the hypotheses of all the things that we know, because if there's a proposition and they give you a hypothesis like this converges to something, we need to use that convergence at a certain point. So that information should be recorded. I mean, I'm just writing it out for your benefit, but if you don't write it down, you should at least keep that in mind, and then refer to it when you need it. Okay, so the point here is that you have two things. So we know two things. First is that for all epsilon greater than 0, there exists some n. Again, the epsilons and the n's do not denote the same thing for every single line when I write them down, because they're quantifiers. So for every epsilon greater than 0, there's an n, dependent, of course, on that epsilon. Typically, when epsilon gets smaller, n gets larger, and then such that for all n greater than or equal to n, we have that an, again, minus a, is less than epsilon in absolute value. And we have the same thing for Bn. So again, the epsilons here are variables. They're dummy variables, and we are running over every possible value epsilon at once. So this statement is to be read that no matter what epsilon I put in here, I should get an n, such that the rest holds. And so the epsilons here can be whatever, and here and down here, but to the epsilons up here, to each epsilon here, there's an n of, depending on epsilon, that is not necessarily the same as the n you'll obtain for that epsilon down here. It's just there's one n. That depends, of course, on how fast the two sequences converge to their respective limits. So this is what we know, and what we want to show what we actually want to show is that for every epsilon greater than 0, there exists some n such that for all n greater than or equal to that n, an, so the new sequence is an plus bn, and according to the theorem, the limit is a plus b. So, and this should be then, so the limit is supposed to be a plus b. So the absolute value of an plus bn minus a plus b in parentheses, which is the supposed limit, which is the limit that this is what we want to show. We want to show that the limit of an plus bn is a plus b. Then that has to be less than epsilon. For values of n greater than some n that depends on epsilon, and epsilon is arbitrary. So what do we do here? So we apply the thing to two epsilons. To two different epsilons. So you know that for epsilon over 2, there exists some n1 and n2. Remember that the n's in these two statements above, what we know, need not be the same. So if a sequence converges faster than another sequence, and one can be typically taken to be smaller than the other one. If something converges faster than with a few iterations, there's a few elements in the sequence, you'll be very close to the actual limit. So fast convergence means that these capital N's can be taken to be smaller. If it converges slowly, on the other hand, then you can typically expect it and becomes it's very large for small values of epsilon. In case you have n1 and n2, one corresponding to one sequence and the other one to the other sequence, such that for all n greater than or equal to n1, an minus a is less than epsilon, and for all n greater than or equal to n2, bn minus b is less than epsilon over 2 and epsilon over 2. Remember, epsilon over 2 satisfies the same conditions that we have for both statements involving the convergence of these sequences. So epsilon is any number greater than 0. If epsilon is a number greater than 0, then certainly epsilon over 2 is going to be a number greater than 0, so you can plug it in here as a valid input, and you should get the existence of an n, so not associates epsilon to epsilon over 2, such that for any n greater than or equal to n, a sub n minus a in absolute value is less than epsilon. And the same thing here applies for the second statement. Okay, so we have these two things are true. So this implies actually that if if n is greater than or equal to the max, to some n, 0 or n, just n, I mean, which we're going to define as the maximum between this n1 and n2, n1 and n2, then both things are gonna be true at the same time, both of these statements, so this one and this one. One requires n to be greater than or equal to n1, the other one requires n to be greater than or equal to n2. And both are statements for the same epsilon over 2. So the n's here for which beyond which an is sufficiently close to a, I mean within an epsilon over 2 neighborhood, is n1, and the value of n beyond which all the elements of the second sequence are within an epsilon over 2 neighborhood of b is n2. But of course, if n is greater than or equal to the maximum between these two numbers, then both of these things are going to be true. That a n is within an epsilon over 2 neighborhood of a, and bn is within an neighborhood epsilon over 2 neighborhood of b, meaning the distance with respect to the respective limits is less than epsilon over 2. Okay, so once we've noticed that, then we can complete the proof. So remember what we were given? We were given arbitrary epsilon greater than 0. So this is what we have. So we start with epsilon greater than 0. So we should start with that. So just to be more organized. So whenever we want to prove something like this, we have to start with an arbitrary value of epsilon greater than 0. And after that, I mean, you do some things with epsilon and use the hypothesis in the way that you need in order to exploit the properties that you know for sure you have, and so as to conclude what you want to show. So you have these two statements are true for values of n greater than or equal to n, and so we can say then, remember that we started with an arbitrary value of epsilon greater than 0, and what we can say then is that an plus bn minus a plus b, which is equal to, this is what we want to show that is less than or equal, I mean less than epsilon, when n is greater than or equal to n. And this is just equal to, we're going to just open the parenthesis and group this term with this one and this one with this one. So an minus a plus bn minus b. And here we use the triangle inequality, and we get that this is less than or equal to an minus a in absolute value plus bn minus b in absolute value. And this is the important part now. So remember that we wanted to give ourselves an epsilon that was greater than 0 and conclude that for values, we wanted to show the existence of an n, capital N, and this is our capital N. This is the capital N that we propose. And we want to show that if n is greater than or equal to that, then this distance here is less than epsilon. And this is what we're going to be able to show, because this is going to be less than epsilon over 2. So the first, so this absolute value of an minus a, the absolute value of an minus a sub n minus a, is going to be less than epsilon over 2, and the second expression here as well. as long as n is greater than or equal to n. Remember that if n is defined as a maximum between n1 and n2, and for all values n of n greater than or equal to n1, an minus a is less than epsilon over 2, and for all values of n greater than or equal to n2, bn minus b is less than epsilon over 2. So that means that and this is this difference here at the beginning is going to be less than epsilon for values of n greater than or equal to n, which is what we wanted to show, right? So we started summarizing in sum. We started with a given epsilon, gave us some epsilon. We used the hypothesis for and used the the knowledge we had of the convergence of an and bn to their respective limits, and we applied it to a particular epsilon. So that statement that holds something that holds for every positive number, so any possible positive number epsilon. We use it for a particular number epsilon. Here, unfortunately, we're using the same notation, but this is epsilon over 2. Right, so this is going to be, so here we're applying the statement for every epsilon up to epsilon over 2. If you think of the other epsilon as some vague epsilon, and this one as some epsilon 0. And then we're applying it to epsilon 0 over 2. And then we found an n. So given an epsilon, we find an n that depends, capital N that depends on some epsilon, which is what we did, for which this difference here, so this difference here is less than epsilon whenever n is greater than or equal to that capital N. And this is exactly what we accomplished. So this is the proof of the proposition. So part 3 and 4 are going to be left to you as exercises. So 3 and 4, so the product and quotient are going to be left to you as exercises. So you should so the proofs are left as exercises. Okay, so that's what we're going to do. You're gonna work on these exercises, and I'm gonna assume that you work on them and you understand the proofs, or at least look at the proofs and try to reproduce them yourself without looking at the book. And after that, then we're going to continue with with the analysis. So now that we have the order limit theorems, we'll continue with the squeeze theorem, which is the a very important thing that you learn in calculus. You used it many times. And yeah, so the basically says that if you have a sequence which is trapped between two sequences, and those two sequences have the same limit, then the sequence in between has the same limit as the two outer sequences. Okay, and we're going to prove that, and that's not going to be such a big deal. After that, we're going to continue with more important properties, like the monotone convergence theorem that I mentioned before. And after that, we're going to show that every bounded sequence has a convergent subsequence. Well, of course, for that we need to introduce the notion of subsequence. I mean, the actual definition of a subsequence, which is not a difficult concept at all. But so that's the way we're going to do things, and then we're going to assign some reading and a lot of exercises for you to work on. Okay, so that's it. I'll see you in the next video.